Hi everybody, welcome to our video on linearization and differentials. This is our fourth video in our applications of derivatives series. So we're going to start off by talking about linearization. We've seen that a tangent to a curve at a point is a straight line that passes through that point with the same slope as the curve at that point. So first of all, I'll direct your attention to the chart on the left-hand side. It's a plot of y equals x squared with that curve shown in blue. And there's also a tangent to the curve at the point 1, 1, highlighted in red. So our tangent is passing through that point 1, 1. The right-hand chart is the same data, but it's zoomed in on the point 1, 1. So we can see on that chart on the right hand side that close to the point the tangent line has similar values to those of the curve, and where the values are similar we can use the tangent line to approximate the values of the curve. So our tangent line at the point 1, 1, that's a linearization of our curve at the point 1, 1. And we can use these linearizations to do different things, which we're going to talk a little bit more about. So to talk about linearization and differentials, we can use linearization to approximate a more complicated function with a simpler one that's easier to work with. With linearization and differentials, we can perform error analysis and estimate the sensitivity of a function to change. So what we're going to do is we'll discuss linearization further, and then we're going to move on to discussing differentials and their uses. So, to focus on linearization, if a function f is differentiable at a point x equals a, then the linearization L of x is given by the following equation. So L of x is equal to f of a plus f prime a multiplied by, in brackets, x minus a. So it's worth looking at this equation and just thinking about what each of these terms is. The linearization is L of x. So f of a, that's the value of our function f, where x is equal to a. F prime a, that's the derivative of our function f at the point where x is equal to a. And in brackets x minus a, that's the difference between a value of x and the value of x at a. The L of x, that's the linearization of the function f at a, and the point x is equal to a, that's referred to as the center of the approximation. So if we think about our previous slides, where we had that y equals x squared curve, and we had the tangent to the curve at the point 1, 1, well, the center of our approximation, that was that point 1, 1. That was where the tangent was intersecting with that curve. And if we look at the chart on the right hand side here, we've got a function y equals f of x highlighted in blue, and we've got a tangent line highlighted in red. So our red tangent line, that's our linearization of our function, where the linearization's been defined at the point a, f of a. So what we could do is we could use that linearization to estimate values of the function f of x. Say our function was say really complicated and difficult to work with. If we really didn't want to work with that function, well, in certain cases we might be able to work with the linearization instead, if that linearization is a little bit easier to work with. That can make our work easier. If we look further at the chart, we see that different parameters have been highlighted. We've got the point a f of a. We've also got the x value a plus dx. So the change in the function delta f going from x equals a to x is equal to a plus dx, well, we work that out as f of a plus dx minus f of a. But we can also estimate what the change in the function would be going from x is a to x is a plus dx by working with the linearization. So by working with the linearization, the change in the function from the linearization, delta L, that's going to be equal to f prime a dx, where f prime a is the derivative of the function at the point a multiplied by dx, where dx is the change in the value of x. So we're going to see more about this as we continue. So for an example, say we want to find the linearization of f of x where x is equal to 0 and where f of x is equal to the square root of x plus 1. Well, we can find the linearization L of x at a point x is equal to a using the equation L of x is equal to f of a plus f prime a multiplied by x minus a. So here with this equation, our L of x, that's our linearization for a given value of x. F of a, that's the value of our function f for an x value equal to a. F prime a, that f apostrophe a, that's equal to the derivative of our function f where x is equal to a, and then x minus a is the difference between those two parameters. So at x is equal to 0, we can work out what each of those variables is. So f of 0 is equal to the square root of 0 plus 1 from our definition of f of x is equal to the square root of x plus 1, which works out to be the square root of 1, which is equal to 1. Our f prime x, the derivative of f with respect to x, that's equal to a half multiplied by x plus 1 in parentheses raised to the power of minus a half. So our derivative where x is equal to 0, f prime 0, that's equal to a half multiplied by 0 plus 1, where that's raised to the power of minus a half. That works out to be 1 over 2 root 1, which is equal to a half. So now we have the terms that we need to substitute into our linearization equation. So L of x is equal to f of a plus f prime a multiplied by, in parentheses, x minus a. When we sub in all the values that we've just worked out, we get that L of x is equal to 1 plus a half, all multiplied into, in parentheses, x minus 0, which works out to be 1 plus x over 2. So what we've just done here is we've worked out that for a function f of x is equal to the square root of x plus 1, we can approximate the values of that function using the linearization L of x is equal to 1 plus x over 2. So if we're very, very close to x values of 0, we can expect that this approximation should give us quite accurate estimates of the value of f of x. And we can test this now. So for x values close to the center of our approximation, which was x is equal to 0, the approximation agrees well with the function it approximates. For x is equal to 0.01, our linearization L of 0.01 is equal to 1 plus x over 2, which is equal to 1 plus 0.01 divided by 2, which is equal to 1.005. So that's our estimate based on our linearization. Well, the actual value of the function f of 0.01, that's equal to the square root of 0.01 plus 1, which is equal to the square root of 1.01, which is equal to 1.00499. So, as you can see, these values are very, very close together. But we also see that using x values further away from the center of the approximation results in a loss of accuracy. So the estimates that we can make with our linearization, they're not as good if we start getting further and further away from that center value. For example, previously we were 0.01 units away from our center. In the example at the bottom of the slide, we're one integer away from our center. So our center is 0, and here we're working out L of 1, which is equal to 1 plus x over 2, which is equal to 1 plus a half, which is equal to 1.5. So our linearization is estimating that the value of the function is going to be equal to 1.5 for a value of x equals 1. But in actual fact, the value of our function f of 1 is equal to square root of 1 plus 1, or square root of 2, which is equal to 1.414. So now that we've gone a whole integer away from our center x equals 0, the difference between our linearization estimate and the actual value of the function, it's significantly different compared to when we were really, really close to our center x is equal to 0. So we've seen how linearization can be used to approximate the values of a function. We're now going to learn about differentials. We can use differentials to estimate the change in a function f for a given change in the input variable dx. So for a differentiable function y equals f of x, we've expressed the derivative previously as dy dx, which is equal to f prime x. So on the left hand side of the equal sign, that's the Leibniz notation dy dx, and on the right hand side of the equal sign, that's the prime notation f prime x. Well, we can also think of that Leibniz notation dy dx, we can actually think of that as a fraction, and we can move that dx over to the right hand side of the equation. And when we do that, we say that the differential dy is equal to f prime x dx. So our differential dy, it's equal to the derivative of the function f at some value x multiplied by the change in x. So what we'll see is that we can think of our differential dy as the estimated change in y is equal to the derivative of x, or the derivative of f prime x multiplied by the change in x. So here's an example of how to calculate the differential dy. Say we had y is equal to x cubed plus 10x. Well, our formula is dy is equal to f prime x dx. F prime x is equal to 3x squared plus 10 using our differentiation rules. And plugging that into our equation, our differential dy is equal to 3x squared plus 10 multiplied by dx. So we can use differentials to estimate the change in the function f for a given change in the input variable dx. So the estimated change in the function f, that's going to be equal to dy for a given change in the input variable dx. So the differential dy is equal to f prime x dx at a point x equals a. That represents the change in the linearization of f corresponding to a change dx in x. So the differential dy is equal to f prime x dx at a point x is equal to a represents the change delta L in the linearization of a function f corresponding to a change dx in x. So if we look at the chart here, we've got our function y equals f of x highlighted in blue. And then we've got a tangent to that curve with the tangent at the point a f of a, and that tangent line is highlighted in red. So that tangent line, that's our linearization of the function y equals f of x, where that linearization, its center of its approximation is at a f of a. And the change in our function delta f going from x is equal to a to x is equal to a plus dx, that can be worked out as f of a plus dx minus f of a. Alternatively, we can estimate what that change in that function is going to be using the change in the linearization over that change in x values, which is equal to f prime a multiplied by dx. So that change in our linearization, that's our differential there. So our differential is our change in our linearization of our function. So we can use the change in the linearization of f to approximate the change in the function f over a given dx, where dx is small. Because as we've seen, as we get further and further away from the center of our approximation, typically the accuracy of our estimate, it begins to drop off. And you can see that here on the chart. Close to the center of the approximation, the point a f of a, the values of the red line are very, very close to the values of the blue line. And they're almost, very hard to differentiate the two close to that point. But as you get further and further away from the point a f of a, they increasingly diverge. So for small values of dx, the differential dy, which is equal to the change in the linearization delta L, and delta f should agree closely. So for small values of dx, the differential dy and delta f should agree closely. So we can see that with some examples now. We're going to do some estimates of change using differentials. Say we want to use differentials to estimate the change in the surface area of a sphere when the radius increases from 10 meters to 10.1 meters. Well, we start with our equation for surface area of a sphere. Surface area S is equal to 4 pi r squared. So our differential ds, that's going to be equal to the derivative s prime r multiplied by dr. And working that out, that comes to 8 pi r multiplied by dr. Well, we have a radius value r equal to 10 meters. And our change in our radius dr, that's equal to 0.1 meters. So we can sub all these values in and work out what our differential is. So our differential ds is equal to s prime r dr, and substituting in we get 8 pi multiplied by 10 multiplied by 0.1, which is equal to 8 pi. So we've estimating using differentials that the surface area of the sphere is going to increase by 8 pi units if the radius of the sphere increases from 10 meters to 10.1 meters. And we can check the accuracy of that estimate by working out what the true change is going to be. So we can do that now. The true change in the surface area is given by 4 pi multiplied by 10.1 squared minus 4 pi multiplied by 10 squared. That works out to be 102.01 minus 100 multiplied by 4 pi, which works out to be 8.04 pi. So you can see that the differential estimate of change agrees closely with the true change in surface area of the sphere. So to talk a bit about absolute, relative, and percentage change, we can describe the change in a function f in a number of ways. We can describe it in terms of absolute change, where the true absolute change, here we'll describe it as delta f, is equal to f of a plus dx minus f of a. We can also estimate the absolute change using differentials, as the differential df is equal to f prime a multiplied by dx. So we can also look at the true relative change, where the true relative change is equal to the true absolute change, delta f, divided by f of a. And we can also look at the estimated relative change as the differential df divided by f of a. We can examine the true percentage change as the true absolute change, delta f, divided by f of a multiplied by 100. And we can also examine the estimated percentage change using differentials as the differential df divided by f of a multiplied by 100. So you can see here with this table that we can use differentials to make estimates of absolute, relative, and percentage change. And we're going to see a few of these estimates now. So here's an example. With our expanding spheres, we're going to have a similar example to previous. We've got our sphere with our radius of 10 meters. If the radius expands from 10 meters to 10.1 meters, so the same expansion as last time, what will be the relative change and the percentage change in the volume of the sphere? So previously we were estimating the absolute change in surface area. This time we're going to look at the relative change and percentage change in the volume. So we start with our function for volume of a sphere. V is equal to 4 over 3 pi r cubed. Our derivative, dv dr, that's equal to 3 multiplied by 4 over 3 pi r squared, which is equal to 4 pi r squared. So from there we can work out that our differential dv, that's equal to 4 pi r squared dr, because it's equal to the derivative multiplied by dr. We've got our derivative is 4 pi r squared, and we multiply by dr. So we see from our table that the relative change can be represented as dv over v. So we know dv is equal to 4 pi r squared dr, and we know that v is equal to 4 over 3 pi r cubed. So dv divided by v works out to be 4 pi r squared dr all over 4 over 3 pi r cubed. And when you cancel out those factors, you get that is equal to 3 multiplied by dr over r. So if you remember that dv over v is the relative change in V, and dr over r is the relative change in r, here we've got dv over v equals 3 times dr over r. So we can see that the relative change in v is equal to 3 times the relative change in r. So if the radius r increased by 1%, as it did here, then the volume will increase by 3%. Here's another example with regards to error analysis. If we can measure the length of a cube with an error less than or equal to 2%, what will be the error in our calculated surface area and calculated volume of the cube? So we can work this out by calculating what the relative change in the surface area and volume would be for a known change in the length of the cube. And to do this, we use differentials as before. So we start off with the surface area on the left hand side. The surface area S is equal to 6 multiplied by the area of a side, which is length squared, because there's 6 sides to the cube. So our derivative ds with respect to dl, that's equal to 2 times 6 multiplied by length, using our power rule. So our differential dx, bringing that dl over to the other side of the equation, we get ds is equal to 2 times 6 times length multiplied by dl. So if we divide on both sides by s, we can work out what our relative change is. So we get the relative change in surface area, ds over s, is equal to 2 times 6 length dl, all divided by 6 length squared. And that all cancels out to be equal to 2 times dl over length. So our relative change in surface area, ds over s, that's equal to 2 times the relative change in the length, dl over length. So we can see from the workings on the left hand side above that the relative change in surface area S is twice the relative change in length L. So our error in calculated surface area S will be 2 times the error in the length 2%, which is equal to 4%. Now I direct your attention to the workings on the right hand side, where we look at calculated volume. So we start off with our equation for volume of a cube. V is equal to length cubed. Our derivative, dv dl, using our power rule, that's 3 length squared. So our differential dv can be worked out by bringing dl to the other side, where dv is equal to 3 times length squared multiplied by dl. If we divide by v, now we can work out what the relative changes are. So we've got dv divided by v is equal to 3 length squared dl divided by volume of a cube, which is length cubed. When those length terms cancel out, we get that the relative change in volume, dv over v, is equal to 3 times the relative change in length, dl over length. So we can see from the above workings on the right hand side of the slide that the relative change in volume v is 3 times the relative change in length L. So our error in calculated volume v is going to be 3 times the error in the length, 2%, which is equal to 6%. So what we've seen here is we've seen a few different things. We're focusing on applications of derivatives, and we've seen that we can use derivatives to work with linearizations of functions, and that we can use linearizations to make estimates using differentials. And we've worked through a number of different examples using differentials to make estimates of change and also to do error analysis. I hope that you found this video useful. Thank you for your time, and see you next video.